Hi, in this Let's Create series we're creating a 2D jigsaw puzzle game like this. In the last episode we created all of the individual pieces, and in this one we're going to scatter them around the board and create an area for you to assemble the jigsaw. Let's get started. Starting with the jigsaw fully assembled somewhat ruins the joy of a jigsaw puzzle, so we need to scatter the pieces across the board. To this end, at the end of our start game method, we're going to call a new scatter method. We want to place our pieces randomly around the screen. In order to do this, we need to know where the valid coordinates to put our pieces are. As we're using a 2D orthographic camera, we can get the height directly from the camera. Use camera.main.orthographic size. This will be 5, as that's the default orthographic size and we haven't changed it. This is half the height. 0, 0 will be in the centre, the top edge is at +5 and the bottom at -5. To calculate the width, we need to know the aspect ratio of our screen. This is the screen width divided by the screen height. We need to cast the width to a float because these are integer values. If you didn't, you'd get an integer truncated value as an output. You don't want this. If you had a 1080 setup as 1920 by 1080, this is an aspect ratio of around 1.77. We really do need that floating point precision. If this was rounded down to 1, that would be really bad. So, the orthographic width is now our screen aspect ratio multiplied by the orthographic height. Now we know where our pieces can go, we can place them. Using a for each loop, we iterate over all the pieces in our pieces array. This is one of the reasons we saved them to this array, as we were creating them. You could scatter each piece as we create them, but trying to do everything at once can end up with large methods. Separating things out entirely when possible is often a good idea to keep your code easily maintainable. We need to generate a random x coordinate. For this, we can use random.range with a minimum value of minus the ortho width and a max of ortho width. Similarly for y, between minus ortho height and ortho height. Then we set the piece position to a new vector 3 using our random x and y values. Again, just -1 for z ensures it's in our camera clipping plane. This would be perfectly fine. However, you can get unlucky like I have in this example here. You can see that one of the pieces has gone off the edge. This is because the unity piece position is the center of the piece, so at the extreme random values the pieces will be half off the board. To correct this, we can just adjust our height and width variables to make sure that doesn't happen. Firstly, we need to work out the size of each piece. This is our width and height global variables. However, we need to ensure that we get the true size, so we need to multiply this by the game holder's local scale. As you remember, we set this to make sure our pieces were a decent size for the screen. We could have equally used any piece from our array and taken the size directly from that. Each method gets you the same result. Now we have the piece width and height, we simply update our ortho height by subtracting the piece height. And for the ortho width, we subtract the piece width. If you like, you can just subtract half the width, which would allow the pieces to go up to the edge but not past it. However, I like that all the pieces are a little further from the extremities. Back in Unity, we can see this in action. When we select our puzzle, the pieces are scattered around the board for us. Nice. The next job is to set up a location to drag the pieces to for the completed puzzle. If you have the top right piece, it'd be really useful to know where that goes by having a visual border. To do this, we'll use a line renderer. On the game holder, click Add Component and select the line renderer. We'll do a bit of setup of this here in the inspector, then finish off the rest in code. Firstly, we want a border, so this will need 4 points. Expand the positions element and set the size to 4. I'll just put these as some placeholder coordinates so we can see what we're doing. The actual coordinates will be set in the code, as they'll depend on the shape of the jigsaw we're doing. Whilst we're talking about coordinates, we should uncheck Use World Space, which is on by default. This will simplify our code, as we won't have to worry about whatever scaling the game holder is doing. The first thing you'll notice is that it's pink because it's missing a material. Let's create a material for it in our materials folder. Right-click, create material, and we'll call it border material. We just want a simple colour, so set the shader to unlit texture. Now, back in the line renderer component, we can set the material to the one we've just created. Now the second problem is that this isn't a border because it isn't a closed loop. The line renderer doesn't automatically join the last point back to the start. To enable this, we check the loop option. Finally, it's obviously too chunky. We could change this here using this little graph. But I find this mightily annoying to get the exact value I want, so we'll ensure that this is set in the code. We don't want the border to always be showing, so we disable the line render component for now using the checkbox by the component name. We'll turn it on in the code when we want to show it. Jumping back into the code, at the end of our start method, we'll add a new update border method to set the final parameters for this when we start the game. The first thing we'll need is a reference to the line renderer. We get this by calling getComponent on the GameHolder object with the type line renderer. To put each point of the line renderer into the correct position, we need to know how big the jigsaw is. As the jigsaw is centered at the origin, the vertices on the left will be at negative half the width. We can calculate this as width of our individual puzzle piece times dimensions.x, which is how many we have, and then we simply divide by 2 to get half of that. The same logic to get the height can be done. Height times dimensions.y divided by 2. Again, height times dimensions.y is 1 by definition, so we could simplify this, but we leave the calculation here to make it clear in case you change the decisions I made earlier. The z value will set to 0. So for each of the vertices of our border, we need to set one of the line renderer points. Use setPosition to do this. The first parameter is the index of the point in the line, so 0 is our first. Then for the position, we create a new vector 3, and we'll start at top left with negative half our width and half our height with our fixed z value. Then we'll go round clockwise. Point 2 is half width and half height. Point 3, bottom right, is half width and negative half height. And finally, point 4 is negative half width and negative half height. 2 points to note here. This works because we set up our line renderer to have 4 points in the inspector. If you didn't, these positions wouldn't exist for you to set the position. Secondly, we use border z as 0 here to make sure our border is behind our jigsaw puzzle pieces. They were created at negative a small amount, so having z larger at 0, we ensure that the line doesn't show on top of them, which would look weird. Now we can also set the line renderer width here. It is in fact 2 variables, start width and end width, because the line renderer supports tapering of the line. We set them to 0.1, which looks good to me. Finally, we enable the line renderer by setting Enabled to True. This means when we click on a puzzle to solve, we can show the relevant border after it's all been set up. So let's jump back into Unity to check that out. Firstly, I'll click on a horizontal puzzle. You can see it's behind the puzzle pieces and the right sort of shape and size. Then exiting and trying a vertical cake, you can see that it's working too. That's it for this episode. I've split this series up into smaller chunks to hopefully aid your learning. In the next episode, we'll implement the dragging of the jigsaw puzzle pieces and a snap mechanism that puts them in exactly the right place when you get close to the real one. This will bring the game to life. As ever, the full code is on GitHub and linked in the description below. See you next time.